So hopefully, well, maybe everybody here was here for my last talk. Don't have to repeat my entire introduction, but very briefly, um, some of the context for this talk here. When Julia introduced threads and we added @spawn and such, at the time the entire focus was on high performance computing and supercomputing stuff, scaling things really high. Throughput was what it was all about, and efficiency. Since then, I now work for relational AI, and relational AI is writing a server application. Our parallelism is utterly different. We are not focused on processing large chunks of data with parallel loops. We have functional parallelism, where we have groups of tasks doing certain operations and other groups of tasks doing other operations, and they feed each other and communicate back and forth. The challenges are completely different, and what you want from your underlying parallelism is also quite different. And one of the things you want is fairness. So here's your server application to set context, right? If you squint a lot, this is sort of what any server application looks like. You have requests that come in. You have a processing pipeline, which 10,000 feet up looks sort of like our application looks a bit like this. We compile a request that runs in one task. Then we run some optimization on that, and then we feed that to a query evaluator. And that evaluator runs a whole bunch of tasks. Those tasks are basically going to operate on data, and so we have like this cache, this pager cache thing, which goes off to the cloud and streams in data, which it has a 3-level cache, so it comes from the cloud to local disk to local memory, and there's a whole bunch of tasks managing, fetching pages from the cloud, writing dirty pages back to the cloud, and so forth. So there's a whole bunch of tasks here in this pipeline. So the question you want to ask is, in what order should these tasks run? Especially when you add the other twist that there are multiple requests which come in at different times, and so there are tasks for each of these requests. So in what order should these run? And in what order will they run? So I will assert here and talk about both these points in more detail in the rest of the talk. So tasks should be scheduled in the order they become ready to execute. First in, first out for fairness. Now, I don't know that people will argue with this necessarily, because your last thing you'd want is when you go to the DMV to anybody who comes in after you gets to go first. So for fairness, you definitely want FIFO. And another aspect of fairness is that a task should get its fair share of runtime. It's especially annoying when you're behind somebody who takes 20 minutes with the representative that you're waiting for to talk to for 10 seconds. So both of these are necessary for fairness. Julia's current task scheduler, as I said, was not really designed and planned thinking about this particular aspect of parallelism. The current task scheduler is a priority scheduler. It uses multi-queues. I have all these citations over here. I don't have the clever QR codes. I have to figure out how to start doing that. But yeah, so it was inspired by parallel depth first scheduling, which is an approach that is provably cache efficient for parallel code. And as it says here, it was intended to be efficient in time and space, specifically for nested parallel programs, because one of Julia's key advantages is composability, where you can take different packages that are not even necessarily aware of each other and work and have them work together. So if you are starting a parallel loop in one package and you have a parallel loop in another package, then you want them to compose well and throughput to work well. So there's a lot more in talk you can look up on YouTube, shared memory parallelism in Julia. So what's the problem? The problem is that the idea was based on a research topic, parallel depth first scheduling. Additional work is necessary to evolve this further, to improve our ability to actually achieve this depth first schedule, and that work has unfortunately not really happened. So it's a priority-based scheduler. Tasks do, in fact, have a priority field, but we don't use them. And the reason we don't use them is because as soon as you introduce priorities into a system, you open the door to starvation. Your high priority tasks hog the cores, and your low priority tasks never get to run at all. And debugging this sort of thing could be a real nightmare. There are solutions, but we actually have to develop those to detect starvation and to deal with starvation, aging, and so forth. So right now, Julia's task scheduler uses this elaborate, very scalable priority queue, but we don't use priorities at all. Excuse me. But then the question that I only started asking in industry is our task scheduler actually fair? If you go back to our server application, how do those tasks get scheduled? What's the ordering over there? When we first wrote this, as I said, the focus was on depth-first scheduling, not on fairness. So partly due to these lack of development in depth-first scheduling, there's been a push now, there's an open PR on Julia to add a work stealing scheduler. And this is, there's nothing wrong here. This is a well-known thing. There have been multiple languages that use this in the past. It's efficient in time, space, and communications. The idea is very simple. Each thread has a deck. It pushes and pops tasks from the head of the deck. And when its deck is empty, it tries to steal from the tail of some other thread's deck. There's aspects to this, but fundamentally that's what happens. Now here's the key here. If you push and pop from the head all your tasks, that's last in, first out. Last in, first out is great for locality because you're running your recent tasks. Things that task was doing are probably still in memory, so your cache will work pretty well. But it's terrible for fairness because your older tasks can end up waiting indefinitely if new tasks keep being added, right? Yeah. So for people who were at my last talk, this is sort of familiar. Perhaps it's the exact same benchmark where we have a worker function that's just doing a bunch of busy work, hashes, and periodically yielding. And then it prints its completion sequence running number. So we run 2000 only with spawns of this. And again, we see on Julia 1.10.10 with just 4 threads, you see this blob of spawn sequence to completion sequence, which is again more or less oriented in the opposite direction that we want to fairness. So on our build of Julia, which is a sort of forked, frozen at 1.10.2, but we backport a whole bunch of things. We have some things from 1.11 and such. One of the things we have done is make a change to this behavior. And that change, as you can see, has kind of completely changed the orientation over here, which makes our earlier tasks complete sooner and our later tasks complete later, but it's a bit blobby, as you can see. So what did we do? It's a one-line change. In fact, it's a one-character change. In this file, we go from a less than comparison to a less than equal to comparison. But don't do this at home, because there are problems. There are downsides to doing this. We do improve fairness, right? And this kind of goes into a bit of an explanation. The multi-queue is basically a bunch of heaps, right, sorted by priority. But of course, all the priorities are the same because we don't set priorities. So when you pop a task off the heap, you take the topmost task from the heap. You're going to start running it. Then you take the last task in the heap and put it in the top, and then you sift it down. This is pretty standard heap balancing, right? If you have a less than comparison over there, all the priorities are the same, so less than fails, and then the last task stays as the first task. If you have a less than equal to there, then it will percolate its way back down to where it started. So you get more FIFO ordering if you do this, but you're essentially moving a task, rebalancing the heap on every new task, and on every task schedule, right? So that's costly. The parallel Fibonacci example that everybody loves to show up over here is actually will demonstrate exactly how bad this change can be. With just the less than, you'll see pretty decent performance from Fibonacci. With less than equal to, you'll see terrible performance from Fibonacci because Fibonacci doesn't do any work. It's just spawning tasks, essentially. And every time you spawn a new task, you're doing this heap rebalance on one of the heaps, and so you pay an enormous price in terms of performance. So your tasks have to have a certain thickness, a certain granularity, large enough granularity for this to be worth it. And even then, you pay a bit of a penalty in overhead, but it gives you fairness. So this actually ends up reducing to the old trade-off, latency versus throughput, right? Often they're contradictory, right? Optimizing for one will hurt the other. And this is one of those unfortunate cases that we see with the current task scheduler. Fairness is not usually something we think a whole lot about in HPC, right? It's just throughput. You want to get all your work done. There's not a tremendous amount of ordering constraints. But for the non-HPC world in which I now live, fairness is a very important property. So one question you can ask is, should we just give up on task priorities? Why the heck do we have a priority queue if you're not using priorities at all? Then we just drop this multi-queue and we just use a fast scalable FIFO, and that will give us fairness. And that is definitely something to consider, but just FIFO is not enough for fairness. You also want that second property, which is the fair share of time. Right. So the scheduler switches tasks, notwithstanding Oscar's warning that the scheduler can switch at allocations, tasks can switch at allocations and during GC and such. Yes, it can, but currently it doesn't. Mostly a task will switch when you explicitly yield or when you make some sort of a blocking call which supports that kind of a thing, right? IO, waits, that kind of a thing. So if a task does not yield and does not make a blocking call, it can run indefinitely. If most Julia programmers have perhaps run into this if you're doing heavy compute stuff, that you'll find that a tight loop will essentially hog all your threads and nothing else will make any progress because you were cooperatively scheduled. If your task doesn't yield, then the threads cannot run any other task. So what this ends up meaning is that your tasks will take varying amounts of time. This is that person in front of you taking 20 minutes arguing with the representative when you just have 10 seconds of stuff to do and you can't get it done because it's not fair. So when fairness is lost, your application behaves terribly. And that is definitely not an acceptable state. So is there such a thing as fair cooperative scheduling? Well, theoretically there is. And any PL geeks over here would probably really like this paper. It goes into, small steps, structural operational semantics to prove that cooperative scheduling can be fair. But in practice, it's not that easy, right? You could do things like say, hey, at every time we task switch, we check this task we're switching away from, how much time did it use? Did it use its fair share? Did it use more? Did it use less? And then we tweak its priority so that we are trying to be more fair to the remaining tasks in the system. Unfortunately, as soon as you start doing priorities, we have that other engineering demand where we need to add some support for detection and mitigation of starvation, and we haven't got that yet. But it is potentially a way forward. So there are other approaches, and these are kind of what we are using right now at RAI, where you kind of approximate the fair share by controlling how frequently your task is. It's actually frequency you're controlling. You give a task more runs, and you're approximating the fact that it takes less time than a task which had fewer runs. You still have to defend against starvation in this sort of scenario. There's been some discussion about our thread pools. Now, there are people out there who love thread pools, and there are people out there who hate thread pools. And one could argue that they are not very composable. They're a little difficult to use. And even though there's been proposals for adding user-defined thread pools, it's uncertain whether we should double down on the concept or whether we should move away from the concept in Julia. But if we did have user-defined thread pools, we can sort of, through resource allocation, get some sort of control over how much tasks run. If you have thread pool A with 2 threads and thread pool B with 6 threads, you're giving thread pool B more resources, so it will run more tasks. And so you have some control over there. And then another way you can get a fair share is through preemptive through preemptive task scheduling, which is essentially the idea that it's what the operating system does, and it's what other languages have moved towards, which is the idea that you don't wait for a task to yield or to make some sort of a blocking call. After a certain amount of time, you just forcefully switch away from the task. Go did this, right? Go started with a work stealing scheduler, and there's a heck of a lot of unhappiness with the fairness offered by Go routines and how to architect applications to get proper FIFO fair behavior. And therefore, they introduced a rather elaborate mechanism. They still use work stealing, but they also have a global run queue. So the global run queue is a FIFO. Every new Go routine gets spawned to the tail of the global run queue. And every Go thread pops a chunk of Go routines off that global run queue and puts it into its deck, its local deck. But then it round robins through all the tasks in its deck, right? And the way it does that is through signals. So there's a sysmon that's watching the Go routines running, and it says, hey, this Go routine has already run for 10 milliseconds. Send that thread a signal, and that sig urg is sent to the thread, and then the thread has to then check if this is a safe point at which to do a Go routine switch. And that's not very simple, actually, because there are considerations for what is on the stack. There's a discussion about where safe points are, whether they should do safe points or they should do a conservative stack scan. In fact, there's a surprising amount of overlap between what you have to do for preemptive task scheduling as there is with garbage collection, which also does things like conservative stack scans, or at least the new one. If you attend the talk on Friday about the MMTK work, then you'll probably see a lot more about that. So yeah, there's a bunch of details over here. There's a lot of discussion. When Go actually introduced this, they wrote up a proposal for it, and you can see some of the documentation, which, dating back to Unix. Go look at the source code, and the comments will tell you what's going on in there. But Go took about 2 years from the proposal to actually implementing preemptive task scheduling. And that's with the Go team size, right? And Google's deep pockets. This is not something that we can expect to do in Julia in the near term, or maybe at all. And so don't hold your breath if that's how you're thinking to get a fair share. Some approximation of frequency of tasks is probably, we feel, the way forward. Pursuing priorities and actually starting to use them gives you some more control over fairness and task ordering. Work stealing might be fine for one class of applications, but for a very large class of applications, it is not fine, and we wouldn't want it. I believe Gabriel's PR that's talking about work stealing is in fact structuring it in the form where there's a pluggable scheduler. So you could potentially see a Julia in the future that you can switch schedulers depending on your use case. Not ideal, but it does not really seem like there is one scheduler to rule them all. Going with preemption also adds a bunch of overhead, just to throw that in there, because you have to actually do those switches. So there's no really happy answer over here. This is more like a kind of call to action for people interested in threading, people interested in this problem. We have not definitely got a this is not a solved problem in Julia. There are many things not so great about how we run. Even the interfaces, as you saw in Mason's talk, is questionable. How things are ordered and how things work is another consideration that we would like people to pay attention to, and not just on throughput. And I am very brief with this talk, but I think that's that. Thank you for your attention.
Yeah, we have a full 10 minutes for QA. Okay.
Thank you. So considering this is a difficult problem, why not just lean into the OS scheduler a bit more? Like, there's overhead obviously, but the OS scheduler does fairness, you have priorities, you have preemption. The thread pool solution seems like a good approach that I can see. And you can use work ceiling for anything that doesn't need fairness for the research type jobs.
So the composability challenge is basically if you do not multiplex tasks and allow for the support of potentially tens of thousands of tasks, then you're limited to what the threads can do, right? There are 16 threads on your system, you can only scale so high. Even Linux won't let you create, I mean, it might, but I've never really tried to create 100,000 P threads. But you can create 100,000 Go routines, or you can create 100,000 Julia tasks. How well they work is a slightly different question. The second aspect is, it's pretty fundamental, I feel, to Julia's productivity and usability, this composability thing. There's not, I feel, sufficient emphasis on how powerful that really is. The fact that you can mix and match packages from around the ecosystem and they just work, right? Parallelism is a great way to break that, utterly and completely. So I can go into a little bit more detail unless there's a bunch. But basically, if you're familiar with the HPC world, OpenMP and parallel for loops were utterly and completely broken if you wanted to use them in a nested way, right?
Yeah, the composability, I can see that argument. So we run a company where we have a lot of large jobs that we run for offline kind of research purposes, churning big amounts of data. Fairness is not really a problem. And then we have real-time applications. And in the real-time applications, what we really want is more control over the scheduling and the threading, which is really kind of awkward in the way Julia is set up at the moment. And so that's the direction I was going. But thanks for that.
I'd love to talk after and hear more about that.
Hey, so this example with the custom fork of Julia with the custom scheduler, is that a feasible thing to do when, for example, I have a workload that's mostly like HTTP based, HTTP server based, where the tasks take milliseconds to run? Because I suppose that's the point of the fork, right? How much better is the experience in that kind of workflow with the fork?
Okay. So I put the big red warning sign over there, right? You could try this, right? But there's a reason upstream does not have this change. Okay, the standard behavior of Julia is good for most of the users of Julia today. Making this change could give you benefits. It gives us benefits, right? But in a lot of cases, it's actually going to hurt you. So I'm not, I wanted, that's why I put the big red sign. I'm not advocating that we make this change, no, right? Especially if you have very fine-grained tasks. You know, if something's running for a millisecond or less and then switching, then you're just paying a ton of overhead and not getting a lot of gain. I did not show graphs over here to show performance costs of fairness. I just mentioned them, and I will mention them again. There are performance costs to getting fairness, right? Most recent, last in, first out is great for performance, not so good for fairness, and FIFO is really the other way around. So you could try it, but like I said, there's a reason upstream doesn't do it.
So I was thinking about Workloads that we have in high energy physics, where you have a bunch of things that you need to do, which are very much throughput oriented, and you have another bunch of things to do that you want to run in parallel, where fairness is much more important, and you want to make sure that those threads get constant time slices through the task, and that's one area where at the moment we do use thread pools. I mean, this is actually in C++ that this is mainly done. And the reason is that you basically want to be able to split the scheduling priorities between the thread pools. Mm-hmm. So do you see that as a potential evolution that Julia could support? I mean, it wouldn't be the default, but it could be quite nice for a lot of problems. It's sort of like, I'm going to give 2 threads to this. Fairness is really important. Every other thread on the system, I want throughput.
Yeah, so that's the virtue of thread pools, right? That's the reason we should maybe double down on them. The problem is it breaks composability. Every package is going to say, hey, I want a thread pool with 3 threads, right? And I'm going to start all my tasks on my thread pool. Now, as soon as you have 10 packages doing that, you've run out of threads. So we need some way for an application rather than a package to control this. Now, what we've been doing is we call the application the guy starting Julia. That's why we've put the control of how many threads go in the interactive thread pool versus the worker thread pool. We put that on the command line, right? The package doesn't get to control it. The guy running the code gets to control it, the guy who's pulled the packages together. But you can imagine that if you're pulling an application together and you have 16 packages and you're going to have like 12 thread pools, how are you going to set it up? Just starting Julia and passing 16 commas is not the way. Then you're thinking, oh, I need a JSON file or something of the sort to specify how I'm going to configure my thread pools. It gets complicated, and it's not really very composable, which is the negative statement about thread pools. And I don't believe any decision is made. I'm certainly not going to single-handedly make any such decisions, but I don't believe thread pools. I've come to believe that thread pools may not be the way forward. It's rare that we can learn something from C++, honestly. Yeah, they're great for amazing perf, right? If I'm like I said, if I'm at Livermore and I'm strong scaling nuclear simulations, I'm going to write it in C++ and use OpenMP and have nanosecond barriers, but I'm not going to use Julia for that.
I mean, just as a follow-up, if no one else has got a question, we have run into these problems as well, where we have workflows where there are arguments about who the application actually is. So the experiment will say, it's my framework that's the application, but the simulation toolkit will say, but I'm an application too, and I want my own thread pool. And we've definitely run into problems where that's happened. So I do take your criticisms on board. Yeah. It's not an easy problem to solve, but it's a problem that we have, and it would be nice to foresee a solution of some kind that you could employ.
So I don't know if you were at my last talk, but that
I was.
Yeah, okay. So that is possibly, an evolution of task groups. In its current form, what we've put on open source is kind of very basic. It's really more for demonstration purposes. There's many improvements you can imagine to that. But that is a way in which you can use stock Julia and control fairness a little bit. So you set up a task group for the things which care about fairness, and you use, the remainder of, you use other tasks outside the task group to get your throughput. So it's a little tricky. It's not, there's no, as you know, there's no clear, oh, this is the way you do it. But as people solve these problems and can define abstractions which help them solve these problems, we can upstream those and make things better, hopefully. Cool.
Okay, let's give our speaker a round of applause.
Thanks very much.
And we are